Okay, so good morning. Today we're talking about Boolean operators and how we use them in selection. So we've talked about allowing our programs to make a choice, and we've done that in flowcharts with the diamond shape and the if statement. Now we want to make more complex decisions because life is full of complex decisions. Like, it's raining outside. Shall I go outside? Yes or no? Well, it's not just is it raining. It's is it raining and have I got an umbrella? Or is it raining? Have I got an umbrella? And is it worth getting wet in order to get to the canteen in time to get the turkey burger? Like, decisions are more complex than just one Boolean expression. So we want to know what and, or, and not mean and how we can use them with our Boolean operators. How we can use them in our Boolean expressions, because these are Boolean operators. And we want to understand what they mean in terms of logic gates. So George Boole grew up fairly close to where I grew up in Lincoln. There's a statue to commemorate him. He's decided that maths was too complicated with all of these numbers. He decided to simplify it with just two numbers. And he came up with Boolean logic. And it's transformed the way that we do computer science. Even though you've only got true or false, or 0 and 1, you can actually combine them logically to pretty much solve any problem. He was a clever guy, George Boole. You've already come across equality, a test for equality, to say, is your name equal to something or other, or not equal to? But we can combine them by saying and, or, and not. Say, for example, if I'm hungry and I've got some free credit on Uber Eats, then I'm going to order a takeaway. And in Python, we can use them like this. Okay. Life is complicated. Truth tables help us simplify the world. We don't know what's going to happen in 5 minutes' time, but a truth table allows us to predict anything with absolute certainty. I like them. They're beautiful. Here we go. So this is an example. Input A, this could be, am I hungry? Input B, this could mean, have I got enough money? Output could be, am I going to order a takeaway? Well done, yes. So if I'm hungry and I've got money, then I'll order a takeaway. This is the truth table for an AND gate. Let's have a look at OR gates. So this time, I'm not going to use the takeaway analogy here because it would go horribly wrong. I'd order a takeaway if I've got enough money, but I'm not hungry, which seems wasteful to me. So we've been given an example. Is it currently raining? Or is it likely to rain? The output is, shall I take an umbrella? If either of those or both of those are happening, we'll take an umbrella. And then not is much easier. The truth table is much simpler because it's only got one input and it's only got one output. Whatever the input is, the output is the opposite. So it's quite nice and simple. For example, is there a crocodile in front of me? Will I go outside? If there's a crocodile out there, there's no way I'm going outside. If there's no crocodile, I might venture outside. But no, I can't use the word might. It's a truth table. It's logical and it's simple. No room for ambiguity or confusion. If there's no crocodile, I will always go outside. Okay. You can do compound conditional statements, but we'll come back to that later. I would like you, please, to open CT10 in half term 2. First of all, tell me which of these is and, or, and not, and complete the truth tables for all three logic gates. You can answer them in terms of ones and zeros, if the inputs are ones and zeros, or you can answer them in terms of trues and falses, if the inputs are trues and falses. They are both equivalent, thanks to our hero, George Boole. So there is a bit of a mistake in this worksheet. The truth table down here should be written in binary order, as in this is the binary for 0, this is the binary for 1, this is the binary for 2, and this is the binary for 3. So you always see truth tables written in this order. This is like 0, 0, this is like 0, 1, this is like 1, 0. Oops, that's wrong. This should say true, true for 1, 1. Well spotted if you spotted that already. So when we get to activity 2, we have a Boolean operator, a logical operator that combines two inputs. We've got a Boolean expression. This is either true or it's not true. This is either true or it's not true. And this combines our two inputs. The whole expression evaluates into, as in becomes, either true or false. So you can predict whether or not this is true or false, but we need to work out how to get the result. So, I don't know, you can write down true or you can write down false. We shall see. To get the result, let's plot this over here. This time I'm not going to put any code in before. In the past, if you want to find out if it's true, I've told you to wrap it in brackets and print it so that you can display it. Oops, I got my prediction wrong. This time, though, we're going to do it slightly differently. We're going to put no code in and use the REPL, the read, evaluate, print loop, which allows you to just type in a expression like is true or false. Well, surprise, surprise, true is true. 78 is just 78, but is 78 equal to 10? Obviously not. How about this whole expression? If we put that in there, it's false. Why is it false? Well, because 78 is not equal to 10. 6 is not equal to 7. So that's false. That's false. False or false, according to your truth table, if you've got an OR gate, false and false, the output is false. That's where this comes from. Okay, so work your way through each of these Boolean expressions. Let's take a look at activity 3. It talks about compound conditions, and I said we'd come back to that, so here we go. Compound conditional statements. It's basically something that uses more than one logical operator. So we've had things like this so far. Is 3 not equal to 4? Well, yes, 3 is not equal to 4. That evaluates to true. Or, well, to be honest, it doesn't matter what that is. If we've got one input as a true on an OR gate, the result is going to be true. So we've got true or true. We can combine them. They're combined into true. Complex logical statements means that we've got all sorts of things, multiple logical operators, as in more than one and or a not. And it looks rather confusing. So we're going to go through an example on here to help you. This is our logic statement. We have one Boolean expression, a second Boolean expression, the opposite of valid, a third Boolean expression, is the key pressed, the K key, a fourth Boolean expression, the ORed result of that one and that one, and a fifth Boolean expression, the combined result of all of that. How do we do that? Well, in our truth table, we're going to break it down into smaller parts. So, quick tip for you, view and split. Splits word so that we can see that and this at the same time. It's rather helpful. Here we go. I want to see that. And let's see our truth table. Well, what on earth is count? Is count less than 15? No. We don't actually know what count is, but we know that it's not less than or equal to 15. That input is ANDed with something. So as long as that's 0, then the whole thing is going to be false. Because we need both inputs to be a 1, and that input is not a 1. So that is going to be false. That is going to be false. That is going to be false. Let's think about this one. Valid is 0, so not valid. We put that input through a NOT gate to get an output. It's going to be a 1. Oh, I put false. I probably should have put zeros in here. What does this mean? Not valid or key equals k. Well, that's key equals k. Have I got this column or that column? Well, yes, I have actually. So let's check this one. To get all of this, I need that column and that column. And I don't. I haven't got a 1 here. That's why I've got a 0 here. Let's do one more example down at the bottom. Oh, I need to see the kind of title. Come on, Word. Play properly. Let's do this one at the bottom. Is the count less than or equal to 15? Yes, it is. So we might have a 1 here. So is valid, we don't know what valid means, but we know that the input is a 1, so not valid is going to be 0. Is the key equal to k? Well, yes, it is. So have we got not valid or the key equal to k? Yes, we have. We've got that one. So that's a 1. Finally, then, have we got this column, not valid or key equals k? Not valid or key equals k, that's that part, that's that column. Have we got that? Yes, we have. And count is less than 15, that's that one. Have we got this column and that column? Yes, we've got both. So the output is a 1. It looks confusing, The trick here is to break it down and do it column by column. The trick to computer science is decomposition, breaking something complicated down into smaller chunks to work on each of those chunks one at a time. Okay, so for activity 4, we're doing the same but with code. We've got an algorithm here. It says if attendance is more than 85% and if you haven't missed any assignments, then you've passed. Otherwise, you fail. It's a bit harsh, but that's what it says. So therefore, let's split the screen again, view and split, so we can see the algorithm and our test table. Is attendance more than 85%? Well, yes, it is. Have I missed any assignments? Well, yes, I have. So therefore, my prediction is it's going to be a fail. And then when you run it, you can test it. I'm not going to do all of them. So we've had a really good question here. It's not just displaying true or false. We're putting this into a selection statement, if and else. That's the whole beauty of these logical operators. They allow you to make complex decisions using if and else. So let's do one more. I'll do this one. 85. If attendance is greater than or equal to 85%, so that's true, and missed assignments is equal to 0, that's true, then in that case, we've passed. You can test it and see if it actually works. That's your call. Okay, so when you've finished, this is going to get submitted to Half Term 2, Algorithms and Programming 2. And in lessons, we're going to play around with some logic gates.